Welcome, architects and developers. Today, we are diving into the absolute core of LangGraph, defining and initializing state. If you want to build reliable, multi-step AI agents, mastering state management is non-negotiable. Let's get started. Let us begin by defining what state actually is within LangGraph. Think of the state as the central nervous system, or the memory of your application. Large language models, by default, are completely stateless. They have no memory of past interactions. To build an agent that can reason over multiple steps, we must maintain a snapshot of the application's current reality. In LangGraph, the state is exactly that, a central, structured object that flows through your entire workflow. As each node finishes its work, it reads from the state, performs its task, and sends updates back. We typically define the state using Python's typedict or a pydantic base model to ensure that our data conforms to a strict, predictable contract. Look at this flowchart to visualize how state travels. From the start node on the left, an initial state is passed to node 1. Node 1 performs a task like a search and outputs an updated state containing those search results. This enriched state flows directly into node 2, which performs an analysis and updates the state again before reaching the end. The state is the shared payload connecting these isolated tasks. Why do we insist on explicitly defining our state when you are building enterprise AI? Relying on implicit data passing or massive, unstructured prompt strings becomes a debugging nightmare. By forcing you to declare a specific state schema, LangGraph provides ultimate predictability. Every node knows exactly what keys exist. Furthermore, this explicit state is what enables persistence. Because the state is structured, LangGraph can save a snapshot of it after every single step. If an external API crashes, or if you need to pause the workflow to ask a human for approval, you don't lose your progress. You simply load the last state checkpoint and resume exactly where you left off. It is the foundation for fault-tolerant, multi-agent collaboration. This diagram contrasts implicit versus explicit state. On the left, traditional chains use implicit data passing, making complex loops hard to debug and impossible to cleanly pause. On the right, LangGraph agents utilize an explicit central state. This architectural choice cascades down into massive benefits, high observability, fault tolerance, and resumable workflows that are essential for enterprise production. Let's get into the code. How do we actually build this? The most common and Pythonic way to define a state schema in LangGraph is by subclassing typedict. You create a class, let's call it AgentState, and you define your keys and their expected types. For example, you might have a user query of type string and an isValid flag of type Boolean. This schema acts as an ironclad data contract for your graph. When a node function is executed, LangGraph automatically injects this dictionary as the first argument. The node can then safely read state, user query, knowing exactly what type of data it holds. This eliminates guesswork and makes your agent's reasoning process incredibly clean. Here we see a class diagram representing our state schema. AgentState inherits from Python's built-in typedict. Inside, we define our specific properties, user query, isValid, documents, and final answer. Every node in our graph will receive an object matching this exact structure, ensuring a consistent data shape throughout the execution lifecycle. Now for a deep dive into a crucial mechanic, reducers. When a node finishes its work, it does not modify the state directly. Instead, it returns a new dictionary containing only the keys it wants to update. LangGraph isolates these state updates safely. But how does it merge them? By default, LangGraph uses an overwrite reducer. It replaces the old value with your new value. But what if you are maintaining a list of actions or a conversation history? You don't want to overwrite history, you want to append to it. To do this, we use Python's annotated type hint. By defining a key as annotated list str, operator.add, you explicitly tell LangGraph's compiler, when a node returns a new list for this key, do not overwrite the old list. Add them together. This is how agents safely accumulate knowledge. This flow diagram perfectly illustrates the reducer mechanic. The current state has a list containing step A. The node executes and returns a dictionary with just step B. Instead of overwriting A, the payload hits our reducer, configured with operator.add. The reducer seamlessly appends the new data, resulting in a new state that safely holds both A and B. With our schema defined and our reducers handling updates, how do we initialize the graph? It is remarkably simple. You pass your schema class directly into the StateGraph constructor, like builder equals StateGraph, AgentState. You then add your nodes and edges, and finally call builder.compile. Compiling is a vital step. It performs structural checks to ensure there are no orphan nodes and prepares the graph for runtime. To actually kick off the execution, you use the .invoke method. Here's the trick. You pass in an initial dictionary representing the starting state. For instance, graph.invoke, user query, hello. LangGraph takes this initial payload, applies it to your schema, and feeds it into the start node. The graph is now live, mutating this state step by step until it hits the end node. Let us trace the invocation sequence. The application calls invoke with the initial user query. The compiled StateGraph catches this and routes the full state object to node 1. Node 1 returns a Boolean flag, which the graph merges into the state. This updated state is then handed to node 2, which generates the final answer. Finally, the graph returns the complete, populated state object back to the application. Let's anchor this in a real-time, high-value enterprise use case, support ticket triage. Imagine building an agent that ingests IT tickets, categorizes them, and attempts to resolve them. Your agent state would be defined with keys for ticket ID, issue text, category, and resolution. When a new ticket hits your backend webhook, you initialize the graph by invoking it with just the ticket ID and issue text. The graph passes the state to the first node, the triage node. The triage node uses an LLM to read the issue and returns category tech. LangGraph updates the state. Your conditional edge then inspects state category and routes the flow specifically to the technical support node. That node executes, finds a fix, and returns the resolution. By meticulously defining the state, we guarantee that data routes flawlessly across specialized agents. Follow the ticket through the system. The invocation payload feeds into the triage node. The triage node updates the state with the category tech. The conditional edge reads the state variable and routes the execution specifically down the left path to the tech support node. The tech support node computes the fix, updates the resolution in the state, and the graph safely terminates at the end node. As we conclude, I want to highlight a massive time saver. Because tracking conversation history is so common, LangGraph offers a built-in state called messages state. If your class inherits from it, you automatically get a messages key pre-configured with an append reducer. You don't have to write it from scratch. You can also use pydantic base models instead of typedicts if you want rigorous data validation at every single node transition. The key takeaway here is that explicit state definition is what bridges the gap between a fragile LLM script and robust, production-grade software engineering. Control your state, and you control your agents. Thank you for joining this deep dive. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Keep building. Our final mind map summarizes the pillars of state management. We start with a strong blueprint using typedict or pydantic. We rely on reducers to safely merge node updates. We initialize the workflow dynamically via invoke. Together, these three pillars converge to create AI systems that are truly production-ready. Thank you for watching.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material. So this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepared for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.